So we are learning about PCP theorem. We will prove the weak version. The weak version of PCP theorem states that NP is contained inside PCP with the amount of randomness that you use is Poly-n and the number of queries made is constant. And the tool that we will be requiring is what is known as Walsh-Hadamard codes. So Walsh-Hadamard codes are nothing but you can think of them. So let's look at strings of length n. Each of them is mapped to a string of length 2 to the power n in a certain way. Okay, so this is 0 1 to the n, this is 0 1 to the 2 to the n. Okay, so there is a mapping. So only very few words amongst this collection of strings of length 2 to the power n will be Walsh-Hadamard codes. The mapping was as follows: WH corresponding to a particular string of length n, let's call it as u. WH of u will essentially be a string of length 2 to the n, and at the ith position of that string, which will denote by WHU of I, this is going to be equal to u product I, and this product is nothing but summation over k varying from 1 to the length uk ik. So ith position is some number between 0 and 2 to the power n minus 2 to the power n minus 1, and that's a bit string of length n. The kth bit of that is ik. Okay. So if you take this dot product mod 2, that's the value at the ith position. Okay. So any string of length n is converted into a unique code word of length 2 to the power n, and that code word is called as the Walsh-Hadamard encoding of u. Okay. So by WHU, we mean the Walsh-Hadamard encoding of the string u. You can also view these strings in 0 1 to the 2 to the n as linear functions. Okay. So look at any string of length 2 to the power n, okay, or any binary string, you can essentially view it as a function from, see, these positions are, if there were k positions, you can think of it as a map from 1 to k to 0 1. Okay, so here the indices are strings. I mean, you can think of them as n-bit strings. So f can be viewed as a function from 0 1 to 2 to the n to 0 1. Okay. And additionally, if it is a Walsh-Hadamard encoding, you can view that these are, you can check that these are linear functions. So Walsh-Hadamard code words are linear functions. Okay, linear functions from 0 1 to the 2 to the n to 0 1. And every linear function is an encoding, or a Walsh-Hadamard encoding of some u. Okay. So if you look at linear functions in 0 1 to the 2 to the n, those can be viewed as encodings of some particular u. So whether you talk about Walsh-Hadamard code words or linear functions, they are one and the same. So this can be easily checked. So now we're going to see some important properties of Walsh-Hadamard codes. If you're given a Walsh-Hadamard code, how do we check whether that is indeed a Walsh-Hadamard code word? Okay. So we argued that we just need to check linearity. Okay. So linear would mean WH code word. Okay. So can we use this to check if a given function or a string, so when we say that this is a function, we think of it as map from the index set to 0, 1. If you think of a code word, we just think of it as a string. So let us take one such function and we want to check if it is linear or not. Okay. So one way would be to check if f of x plus y is equal to fx plus fy for every x comma y. Okay. X can take 2 to the power n different values, y can take 2 to the power n different values. So this would take 2 to the power n times 2 to the power n checks. Okay, or you have to access those many locations. Okay, there are those many possibilities. Okay, so that is prohibitively expensive. But if we check just few positions, we can't be sure that it is linear. Okay. The only way we can be sure that it is a linear function is by checking all the locations in the string. Even if one position is left unchecked, there is only one way that that position can be made into a linear function. So if we give an incorrect value at that location, that will no longer be a linear function. So we cannot get a deterministic algorithm to check whether the given code word is a linear function, but we can get something which is as good, in the sense they are going to be almost linear. Okay, so we will devise a check to see it is reasonably close to a linear function. So that will call for a definition. So we will say that function f and g are row close if the probability of fx being equal to gx when x is chosen randomly from 0, 1 to the power n. If this probability is greater than rho, then we will say that f and g are row close. Okay. They are close by an amount, a quantity rho, if the probability that these functions agree on uniformly sampled point with probability greater than or equal to rho. Okay. So now what we want to do is really check if a code word is row close to some linear function. We will see later on that if it is reasonably close to a linear function, then from that information we can decipher the exact value of that linear function at any point with very high probability. Okay, so that's going to be the local decoding property of All-Shadowmart code. Now we will see how we can check if a given function is linear. We'll need a theorem. This is a theorem by Bloom, Luby and Rubenfield. It says that if probability of f of x plus y being equal to fx plus fy when x comma y are chosen uniformly at random from 0, 1 to the power n. If this probability is greater than some particular amount rho, so let's say if it is this probability is greater than alpha, then f is alpha close to some linear function g. Okay, and this alpha we require it to be greater than half. It's greater than half. Okay. So this theorem states that if you check for just this property, that fx plus y is equal to fx plus fy, if that property is true with with probability greater than alpha, then the function is going to be alpha close to some linear function g. Okay, so this means that we can devise a linearity test by just sampling at few locations. Okay. In the sense, if we run the test of whether fx plus y is equal to fx plus fy for sufficiently many points, that will give us a guarantee that the function f is reasonably close to a linear function. So let's just describe the linearity test. Okay. So first you will choose x and y uniformly at random. Okay, and then evaluate fx plus y, fx and fy. Okay, so this can be directly read from the function. If fx plus y is equal to fx plus fy, this doesn't mean the function is linear, so we will say maybe linear. And if this is not equal to fx plus fy, then we can say definitely not linear. Okay, now we can repeat this test some number of times. So repeat linearity test for, let's say, c by delta times. Okay, so delta is some parameter. If the linearity, after you have repeated it many times, even if one of the tests out of the c by delta test says that it's not linear, then the function is not going to be linear. The code word is not going to be a Walsh-Reinhardt code word. Otherwise, it's going to be, you're going to declare it as, if all the tests had passed, then you will say that it is linear. This is known as, so it's known as a 1 minus delta linearity test. Okay. So for the time being, let's just say that delta equals 0.001. Okay. And if this test comes through, that means f is 1 minus delta close to a linear function with very high probability. Okay. We'll see why is that the case. Okay. So let us say that it is not 1 minus delta close to a linear function. So not 1 minus delta close to a linear function. So suppose this is the case. Okay. Now VLR theorem says that if it is not close, then that probability is going to be less than 1 minus delta. So probability that fx plus y not equal to fx plus fy is going to be less than 1 minus delta. So look at VLR theorem. Since the function is not close to some linear function, that would mean that the probability that fx plus y is equal to fx plus fy is not going to be greater than alpha. So this is not greater than alpha means it's going to be less than alpha. So alpha here is 1 minus delta. Okay, so this would mean that the probability of the function being incorrectly declared as linear is going to be 1 minus delta for one particular run. So if you are running it c by delta times, so probability that 1 minus delta linearity test declares f as linear is going to be less than 1 minus delta the whole raised to c by delta. And this is going to be less than 1 minus delta the whole power 1 by delta the whole power c, which is going to be less than, this inner quantity is less than 1 by e. So the whole thing is going to be less than 1 by c. Okay. So this test called as 1 minus delta linearity test will say that the function is linear with very less probability if the function is actually not linear. You can see that if f is actually linear, the test would correctly predict it to be a linear function. Okay. If it is not linear, if it is not 1 minus delta close to a linear function, then the chances of the function being incorrectly declared as a linear function is very, very small. So we can detect linearity, or we can detect almost linearity. Okay, now this is, we'll see that this is sufficient for us. If it is 1 minus delta close to a linear function with delta, let us say, reasonably high, like 0.001, then we can actually decode that particular linear function. This is called as local decoding. Okay, so we are given some particular function. This might be a corrupted version of a linear function. So f, we will assume it to be 1 minus delta close to f cap. Okay, so f cap is the correct linear function, and we are getting a corrupted version, but these versions are 1 minus delta close. Okay, delta, let's assume that it is greater than 1/4, we can make it even closer than 1/4. But 1/4 itself would guarantee that there is precisely one function f cap. Okay, because this is your function f. There is another function f cap which is at a distance 1/4, which means differs in at most 1/4 bits, and there is another g cap which differs in at most 1/4 bit. Then these both are going to be close by, and they are going to differ in at most half the bits. Okay, so since they differ in at most half the bits, and both are linear function, that would mean that both of them are equal, because each linear function is a Hadamard code word. In Hadamard code words, you can verify that two distinct Hadamard can agree at only at most in half the number of bit positions. So there is a unique f cap to which f is close, and we are interested in knowing the value of f cap at that particular point. Okay. And what will help us is the local decoding. So if you want to compute f cap x, we can essentially use f. Okay. So what we have to do is compute f x prime, okay, where x prime is some randomly chosen point, and compute f x plus x prime. If you choose x prime uniformly at random, x plus x prime is also going to be uniformly at random from 0, 1 to the power n. It's going to be a random string of length n. Okay, although they are dependent. Okay. Now, if we output the value of f of x prime plus f of x plus x prime, okay, we want to know whether this will be equal to f cap x. Okay, we'll claim that that is the case with very high probability. Okay, so we know that f and f cap are close. Okay, so 1 minus delta close. So the probability that f differs from f cap at a point which is sampled uniformly at random, that's going to be less than delta. They agree with probability greater than 1 minus delta. Now, so this value may be different from f hat with probability at most delta. So let me just write down the error probability. This could be incorrect. F evaluated at x prime could be incorrect with probability delta. Evaluated at this point could be wrong with, again, probability delta. Now, so therefore the maximum error is only 2 delta. So these are going to be correct with, so f agrees with f hat at x prime and x plus x prime with high probability, or at least with probability 1 minus 2 delta. So if delta is greater than 1/4, then this agreement happens with probability greater than half. Okay. So in that case, fx prime would be f hat x prime plus f hat x plus x prime, and this is going to be f hat being a linear function. This is going to be f x plus f hat x prime, and since all the arithmetic is mod 2, these two quantities cancel out and you will get this as f hat x. So instead of evaluating the function at a random point x, I mean if you're given a particular point x and you are to evaluate it at that point, instead of directly querying that point, you can check at some related points x prime and x plus x prime, and based on that you can infer the value. So this will be the correct answer with high probability. Otherwise, if you are directly querying, the adversary knows which is the point at which you have to evaluate, and that could have been given the incorrect value. So here, since the adversary has no control over which are the query points, unless he makes large number of incorrect values at various query points, the chance that he will be able to bluff is going to be extremely small. In other words, via local decoding, you can get the correct answer with high probability. Since we are using Walsh-Hadamard code, what we have gained is, first thing, we can check if it is linear. Second thing is we can do local decoding. Okay. We will use these two properties while constructing a PCP for a particular NP-complete problem. So let's just describe the NP-complete problem that we are going to solve using PCP. Okay. We want to show that NP is contained inside PCP, which uses poly n amount of randomness and queries constant number of places. Okay. In order to do this, what we will do is we will take an NP-complete language, and construct a PCP for it. And the language that we choose is something known as quad EQ. Okay. It's the language of quadratic equations over GF2. We'll make it clear what that means. So look at equations of this form. So U1, U2, UK are all variables. So U1, U2 plus U3, U4 plus U1, U5 is equal to, say, 1, and U2, U6 plus and so on. So you have m equations and n variables. Okay, and each equation consists of many terms, and each term is a quadratic term. Okay, quadratic in the sense there are two variables appearing in product form, and a solution for such a system would be assignment of 0 ones to the variables in such a way that the equation holds true, and all the addition and multiplication are carried out mod 2. You can verify that this is NP-complete. That is, we want to know whether this particular system of quadratic equation has a solution or not. This is a circuit SAT can be reduced to this. Okay. So if you can solve this, you can solve any other NP-complete problem. There's an easy reduction to circuit SAT. We're not going to look at that reduction. Okay. So this is the particular problem that we are looking at. Now, how do we solve this using PCP? We will write this equation in a slightly different format. So this has n variables and m equations. We can write this entire system of equations as a matrix, and each ui uj, think of that as a new variable. So let's have a new variable, capital U ij. Okay, and that is defined as ui uj. Okay, so now with this notation, what we have is we can write this entire thing as a matrix. Okay, and these entries, this matrix which we call as A, the entries in this are going to be 0, 1 entries. Okay, because all multiplications and additions mod 2. Okay, and this is going to be multiplied with the vector u. Okay, and u consists of all the capital Uij's. Now, if you solve that, that doesn't mean that the original system of equation, which let us call it as Q. So Q may not have a solution. Okay. We want to solve this equation AU equals B, where B is the vector consisting of all the RHS. Okay. So A is a 0, 1 matrix and B is a 0, 1 column vector. Okay. And U consists of U1, U2, U1, U3, maybe even U1, U1, and so on. Okay. So there are n square entries in U. Okay. So if that has a solution, then we want to say that quad EQ has a solution. Okay. But there is some dependency between these UI UJs. So if additionally, if you say that U is the tensor product of U, where U is a solution. I mean, if you think of the quadratic equation, in that the solution is going to be a vector on n variables. Okay. So if you call that n vectors, I mean, if you call that particular vector as U, so this is a solution to the quadratic equations. Okay. And if your capital U is the tensor product of U and U, okay, then we can say that the quad EQ has a solution. Okay, so let's just write this down cleanly. If AU is equal to B and U is equal to U tensor U for some vector small u over 0, 1, then Q has a solution. This is an if and only if condition. Okay. So here A is going to be M cross n square matrix, U is going to be an n square cross 1 matrix, and B is going to be a M cross 1 matrix. And small u is going to be an n matrix. Okay. And what is this tensor product? So if you take a vector u1 up to uk, and if you tensor product it with u1, u2, uk, you get a matrix which is a k square matrix where the ijth entry is going to be ui into uj. So these conditions you can check that if AB is equal, AU equals B and U is equal to the tensor product of some vector in which the components are chosen from 0 and 1, then Q has a solution, then the reverse is also true. Okay. So what we will try to show is that the solution to this particular system of equations can be converted into a PCP. Okay, so you can construct some particular PCP that encodes the solution of this particular quad EQ. So that's what we will do in the next session.